for the first little while. And I wish that the table here were not higher than lower. So if you guys feel the need, please stand up and come take a look, because I'm going to demonstrate how to make some solutions here with the stuff I've got in front of me. If you can't see, can you get yourself in a spot where you can see? So ignore the notes for right now. I'm not even going to focus on the notes. But you need to be able to see what the heck I'm doing here. So don't hide in the back, I guess is what I'm saying. Wait, first thing I need you guys to make sure you're aware of, when you're working with chemicals at all times, coats, glasses. Okay, I'm okay if you guys are a little bit further back here. I'm not too worried about you getting water in your eyes, but that's my general rule of thumb. Even if it's with something that just seems so simple, it's like you don't need that. Okay, get in good healthy habits when you're in the lab, because I can count on 2 fingers the number of accidents I've had in 10 years of teaching, and I'd sure like to keep that number low. So I mean, don't forget to wear your glasses, because I had a girl who almost got she got acid on her glasses. Would have taken out an eye otherwise. So. Okay, do you guys know some of the tools in our labs here? Like, for example, does everybody know what this is? Yeah, just a basic beaker. Okay. One of the most important tools we'll use is this one right here. Does everybody know what this one is? Okay. This is called a volumetric flask. Okay. And this is a really good lesson to talk about being accurate and precise. I believe I gave you guys a really informal lesson on accuracy and precision the other day. This is a tool that literally has one measurement line on it. You guys can see it. There's just a little white marking right here. See the one right there? It's a little bit different than, say, like a graduated cylinder or a beaker. See how this beaker has multiple lines on there? Okay. This one is calibrated to one line and one line only. However, it is very, very accurate. Okay. This is exactly 100 milliliters if you fill it exactly to that line. Whereas these lines right here, sometimes when they're put on there, they're a little bit more like they're a rough estimate. I wouldn't use this measuring tool and say that if it's measured up to there that it's exactly 20. Just because sometimes these ones are put on there a little rushed. You know what I'm saying here? That's accuracy. To what degree do you actually take the time to make sure that it's exactly perfect? And so this is a more rough measuring tool. But this one you can see, only one line on line. So this gives us a very accurate measurement of 100 milliliters. It's a very useful tool for measuring things. It's called a pipette, and it works very similarly to the graduated volumetric flask here, in that there's also just one calibration line. And again, this is meant to be very, very accurate. And one of the reasons why it's accurate is look at the shape of this tool here versus these 2 tools here. Anybody notice something unique about how these 2 work versus this one? Make it narrower. See how this one's consistent in terms of its, I don't know, radius all the way up here? But these ones right here, the bulk of the liquid's going to go inside the bottom here, and the bulk of the liquid's going to go inside here. And it's very narrow right here. And what that does is if I were to add, say the volume level was supposed to be right about here, if I were to add 1 drop, well, it would raise up just a little bit right here. Is that what I'm saying? But when the volume is right here, if I were to add 1 drop, it's very noticeable. Right, just due to the thin diameter right there. And that same principle applies right here. When you're talking about liquid that's in here, if I add just a little bit of liquid, it goes up so small that you wouldn't even notice it. But this right here would be accurate to the drop, because you're literally going to be able to see the drop of water that makes it so that the line is achieved. You know what I'm saying? So that's why these 2 tools here are actually really useful, because if we're going to make solutions, we want them to be accurate. So what I want to show you guys how to do today is how to make 2 solutions. And maybe the best way of describing this is an analogy of making juice. And I have that on the board here. If you were to make juice, there's 2 main ways you can do it. The first way is you can take solid crystals. You guys can grab stools, by the way. I'm going to be talking for a while, so unless you want to stand the whole time. Should I give you a second here? Go grab somewhere to sit. I want you to be able to see, okay? So if you're hiding at the back, you might not be able to see me work. If you're making juice, really there's 2 parts to making the solution of juice. There's the solute and the solvent. The solute in juice is the crystal light little packet that you pour in there, right? And for us, when we make juice in a solution, that's where I'm going to give you guys some sort of chemical that is just going to be crystals. Say this. Now this is copper 2 sulfate. I picked it just because it's blue. That way it looks kind of pretty. Okay. But that actually leads me to a second rule in the lab. Okay. On lab days, no eating, no food, no drink, because this might look like Kool-Aid. It's certainly not. Okay. So on Wednesday, please don't make any breakfast and stuff beforehand. I know that kind of sucks, but it's not worth it if we're working with stuff that's not safe. So I'll make sure I keep this away from any of you guys that are still eating for now. Wait, so that's one way that you can make juice. You need to take a solute that's solid, dissolve it in water. Solute, crystals, solvent, water. There's actually a second way that you make juice, though, and you might have heard the term like from concentrate. What does concentrate mean in chemistry? Yeah, a lot of solute and solvent. We don't want to use the word strong. Strong actually means something else. What does strong mean? It conducts well, yeah. So strong things conduct, but if we were to talk about drinking this orange juice right here, it is really strong. You know what I mean? Like, it is thick, it is concentrate. I would not eat that orange juice directly out of like the container because it's too much. I've never tried that before, by the way. I was in university. I thought it was a great idea to try eating like the grape stuff. I was like, oh, this is gonna taste really good. I had like 2 bites and I felt sick. Right? Like, it is that concentrate. So those are the 2 main ways of making a solution. Okay. Now, in both cases, we really have to have very, very exact measuring tools because you have a solute and a solvent, both of which need to be measured. Now, solvents, I've already kind of pointed out how we'll do that. A solvent is typically a liquid, but we can measure a liquid right up to that line in this flask. And that way we'll know exactly how much solvent we've used. How do we measure how much solute there is if we're talking crystals? Yeah, we have a scale, right? We measure in grams. So here's a scale. I didn't actually bring the thing to plug it in because I'm not going to worry about that today. But in theory, what we really need to do is we need to take a mass. We need to find the mass of solid crystals. That gets you a mass. Now, if we know what this is, we can find molar mass so that we can convert it to moles, because you can convert mass to moles. Hopefully you know how to do that. And then the issue is, well, how do you get this crystals into this beaker here? So I'm going to show you how to not do it first. Okay. Sometimes what people might do is they'd say, okay, well, I'm going to grab some solid crystals here. They're going to weigh it out. So now it's been weighed. We now have a mass. Let's say it was 5 grams. If you take 5 grams and divide by copper 2 sulfate's molar mass, now we know moles. So now we know how many moles we have here. This is not what we do. Don't pour it inside there. Anyone have any idea why it would actually be a poor idea to pour it inside there? Let's keep walking through the process. What do you do when you make juice then? You've taken your solid stuff and you've put it inside the container. Then you would want to add some water, right? But what else do you usually need to do when you make juice? Just stir it. Even this end of the stick, it's really hard to stir deep down inside there. So because of the nature of how the flask is made, where it's got a very narrow neck, don't pour solid stuff directly into here because it's actually going to cause you major problems. So the first thing you'd actually like to do is just get a small beaker and put your solid into the beaker. This is just a plastic weighing dish. I have tons of these, by the way. They're disposable. You know, we want to make sure that we don't end up with crystals on my scale. Right? Now, copper 2 sulfate's relatively safe, although, I mean, I don't know if you guys can see this one right here, but it is poisonous. Right? So I'm going to make sure I clean up everything afterwards. I mean, it's not going to be poisonous unless I start eating it, right? But, you know, I don't want to go around my lab and see that there's like crystals just lying all over the place because that's a safety hazard. So, all right, now that I've got my solid inside here, usually what we do then is we just pour a little bit of water inside the beaker. Now, this thing is calibrated to be exactly 100 milliliters. So basically all I have to do is make sure I don't fill this flask above 100 milliliters. And again, I don't think this is exact. Like if it says 80 right there, I wouldn't bet my life that it's exactly 80. It's probably 79 or 81 or something like that. But roughing it in this flask right here, in this beaker, is not a big deal, because really its main purpose is that I can stir it. Does that make sense? So pour it in a flask, because that's the easiest way for you to be able to stir stuff. Could someone grab me a quick piece of paper towel just from one of the dispensers? Joe, are you close? Can you grab me a paper towel? I don't want to lay this stirring stick down on my desk right this second here. Normally I wouldn't worry about it if I was in the back there, just because I know that probably not eating or putting other stuff nearby, but this table here is get used for a lot of stuff, so that's okay. So I'm just gonna put this guy down here. Okay, so now another rule that I have in my lab, and I carry this over from my university days. My professors at the U of L, they had a general rule: if you were in the chemistry lab and you had a beaker sitting on the table with a solution inside of it, and you did not write on the container what it was, using like one of the special writing pens, they would dump it down the sink. Okay. And that's just another safety application, because who knows what this is? Who thinks they know what this is? It's probably water. Should you drink it? Do we know this for sure? No. So that's my general rule too. Always grab a marking pen and write on the side of the container what it is. Right? Now it's H2O. Now we all know. Right? Because if that's sulfuric acid, there's a huge difference between the two. Okay? And a lot of liquids, they look clear. So same thing right here. Just to be safe. And really, safety is so important in chemistry. Okay? Like I really do believe that in the wrong hands, this is probably the most dangerous room in the building. I mean, the kitchen and the shop are right up there too. But I mean, if you were to combine the wrong stuff, explosions, toxic gas, poison, like literally, it's all possible, and I don't want that to happen. So, I'll write copper 2 sulfates formula on here just so that I know. As well, I wouldn't want some grade 6 kid to come through here and be like, oh look, they made Kool-Aid. Sometimes it's actually smarter to write it on there before you put the liquid in. Okay, sound good so far? So, recap here. Don't take crystals, weigh them on the scale, and then try to put them directly into here. Put them in a small beaker first. Label the beaker. And I'll be smarter this time. Let's actually label this one as copper 2 sulfate before CSO4. Okay, well now I should be able to fairly easily pour this liquid into here. And steady hands really helps in chemistry. I have funnels for those who feel the need to use them. Okay, and please go ahead and use them at first. But I mean, steady hands is something you'll want to work on over time if you're doing chemistry, because you can't use a funnel all the time. There's a few reasons why. Okay. Did every single solid particle make it inside that flask there? And the answer is no. Every transition you make, you actually would lose a few, because you can see how there's just a little bit of liquid just kind of sitting around the sides here. Well, of all of the solid particles that went from here into here, into here, into here, did they all make it in there? And the answer is again, no. You can even see that there's probably just a few sitting on the edges of this guy right here. And there's a few sitting in there. And so in chemistry, I mean, depends on to what degree we need to be accurate. Because accuracy is how correct you are. But you might even want to do something like this and rinse a little bit like that. See, we can try to rinse all the particles off of here. Switch this up a little more, try to make sure that everything makes it inside here. Now the only rule I've got is I can keep adding more liquid to this, I just can't let it get above the line, okay, because that is my stop line. So I once took a class in university called analytical chemistry, where my whole grade was based on how close my numerical answers were to the correct answer. And a lot of kids hated this class because you had to be meticulous in your work. Right? And sometimes it was painstaking, because you'd be looking at this going, do I see any extra little particles on here that's worth washing? And then you'd go here and do I want to try to make sure that I rinse the whole sides of the beaker down so that everything makes it inside the flask? In that particular class, what the rules were is that you had, like, say, from 1 to 4. They would let you come in early, though, at noon, and you could start washing and prepping all your glassware so that you could just be perfect. Like, before you started, you washed everything, because you didn't want there to be even a slight source of contaminants inside, right? I didn't wash these before. Here. Right? Do you get what I'm saying here? So I want to make sure I show you guys good chemistry, even though it doesn't always matter to us. So let's say, though, that I'm content that all of the solids on here have made it in there now, and all of the solid crystals on here made it in there. The last thing I've got to do is make sure that I get the water exactly up to this line. How do we measure concentration? Solute per solvent. If I'm convinced that all of my solute is in here now, I just have to make sure that I accurately know my amount of solvent. So again, if you feel comfortable with steady hands, you can just start pouring water in the rest. But here's the catch. Don't overshoot it. See how I've kind of left it a little bit there? So that there's a little bit of a gap there? Right. Most people don't have steady enough hands to pour it in like that. So a common thing you'd want is just an eyedropper so that you can try to get it. And this measuring device should be accurate literally to the drop. I don't know if you guys can see this, but as I'm adding drops here, I can visibly see this line here going up like one drop at a time. Now there's some air bubbles in there that I kind of want to fix a little bit too, so I'm just trying to tap the side here. I'm going a little bit faster than I normally should. Does anybody know what a meniscus is? Water has a very unique property in that it can cling to the sides of containers. You can actually see what looks like about the shape of a contact lens at the very, very top. Can you guys see how it looks like kind of a contact lens kind of sitting right there? I'm not the world's greatest artist, but if I were to draw it, here's the sides of the tube. This is where the line is right here. Here's what we're looking for. We're looking for this little curvy kind of section like that for the bottom of it to touch that line right there. Okay. And the reason why is that water will actually cling and pull itself up the sides of the container. It's due to the fact that water is polar. You guys see how there's all these drops just kind of sitting here on the top sides there as well? That's really not ideal because those drops are clinging to the sides. And the same thing sort of happens right here along the edges. Water actually gets pulled up a little bit. So when you want to make sure you've measured it properly, you want to look straight on, and you want the bottom of this little contact lens shape here to be exactly lined up with your line. And I don't know if you guys can see it where you're at right now, but I'm like just shy. So the cool thing about this device is I literally should be able to get it to the drop. Perfect. So far so good. Now we still have a couple other problems though. It's still really not thoroughly mixed. If you were to look at this right here, this top section right here is the water that I've added afterwards. Can you guys even see the discrepancy between the dark blue down here and the light blue up here? This thing needs to get mixed, but there's a couple easy ways to do that. The first is I'll often have some sort of lid. Okay. Now, these lids aren't perfect necessarily, so I also stock in my lab something called parafilm, which essentially is like a special kind of saran wrap. You guys know what saran wrap is? Like you'd use it to seal your food or something in the fridge. So this stuff is flexible, pliable like that, so that you should be able to like stretch it, put it over top like this. And sometimes that's actually enough. If I were to do a good job here, let's be brave now. We're good, right? And so what it'll end up doing is it'll allow you to be able to mix the solution by literally just pushing it upside down and inverting it. If you really want to, you can put the cap on as well. Now, generally in the lab, it's a good idea to try to cap your solutions for two reasons. One, if that happens, we're good. Nothing spilled, right? And it's not uncommon that someone crashes into your stuff. But there's actually another really good reason why too. Over time, what happens to water? Yeah, it evaporates. Now, remember how concentration is based on solute divided by solvent? If your solvent evaporates, we just spent a meticulous amount of time trying to make sure that this was exactly to the line I wanted it there. But even if a little bit of it evaporates, well, now our accuracy is thrown off. So a general idea is you probably want to cap all solutions. Now, one thing you'll notice is that this little contact lens meniscus right here is actually below the line right now. Anyone has any guess as to why it's now below, even though I just measured it was above? Yeah, there's some cling to the sides. There's probably some stuck in like the saran wrap, the parafilm at the top. So that would be normal. That's expected. But hopefully we can do this to stir. Okay. You can't really shove a stir stick through here anymore, but you can just invert it. So that's usually the phrase we use, invert to mix. And now hopefully have a fairly uniform solution. I know it still looks a little different here than it does there. That's probably just due to the fact that this is thicker right here than it is right there. So, but hopefully you guys are in agreement. We've now made a solution. And we should know its exact concentration now because we made it ourselves. We measured the solute, we measured the solvent, we should be able to calculate it. And the word I want to talk about is accuracy. The reason we know it's accurate is because we were meticulous in weighing stuff and we were meticulous in measuring out the volume. Now, the other side of the coin for accuracy is known as precision. Okay, this flask right here is calibrated to 100.0 milliliters. 100.0, not 100, 100.0. The reason why that's important, forcing things. Makes sense. That's your precision. Your precision is how many digits you have. If this thing was calibrated only to 100 milliliters, that's only 3 sig digs. It's actually better for me to show on the scale. If the scale measured to the nearest tenth, and I measured out 1.1 grams, that's 2 sig digs. But if I can measure it out as 1.153 grams, see how I get more digits? That's precision. So accuracy is how well you've actually used your measuring tools. Okay? If I do a sloppy job, and I accidentally, when I make my solution, do this, it's over the line, good enough, first one, no. That's no longer accurate. Does that make sense? But precision is based on how many decimal places this and this tool give you. You know what I'm saying? Another illustration we sometimes use is if I were to have a ruler. Here's a ruler, and this is where the lines are on it. There's a second ruler, has the same lines, only now it gives you like smaller ones in between. This one here is more precise because it allows you to have a smaller incremental measurement. If that makes sense. This guy right here is not a very precise measuring tool. If I asked you to measure out 80 milliliters, I'd probably measure to about there, but how comfortable are you that it's 80.000? Like, do you actually think it's 80.00 right on the dot if you measured it there? Well, no, this is not a very precise measuring tool. But this one right here is very precise. It's accurate if you use it properly. Let me just say that one more time. This measuring tool is very precise. It's 100.0 milliliters, 4 sig digs. That's incredible. But it's only accurate if you, the user, actually use it properly. If you put it up to the line right there, like I've done now, it's no longer accurate. Makes sense. Right. So that's one way of making juice, so to speak. If I go back to my slide here, you pour crystals into water, that's one way of doing it. But there's another way of making juice. It's the concentrate method, where you have something that's pre-made in a concentrated form, and you water it down. Good examples of this would be things like household cleaners or bleach, where you buy it in the concentrated capsules, but like if you were to use it at regular strength, it's way too much, right? And so you have to add it to water to do the same thing. So here's how that method looks in our lab. I'm just going to use this solution now as my concentrated solution. So what you would do is a very similar process. You would want to measure out exactly how much of the concentrated solution you have. You wouldn't just pour a little bit of this into here willy-nilly. You'd want to, again, measure it. But how do I measure this on a scale? It doesn't really work so well. So often we would measure it with volume using the pipette. So here's how a pipette works. It's very clever. You use a pipette bulb, which are these guys here. And, okay, 2 thoughts here. One, these will break. Okay, don't feel bad if they break. Please do your best not to be the cause of them breaking. You need to make sure that you press the up button and inflate the bulb. See how it hopefully will stay like depressed like that. Okay. And then you want to put this on here, but don't like jam it in there so hard that it busts the mechanism. There's a little mechanism in here that allows it to control the pressure. And if you were to do that, you can see how this one here doesn't hold its suction all that well, like it's slowly but surely deflating. This will still work, but please don't like jam it in there so that it's like that far up, like that. That's gonna break. The other thought is that please don't leave them in their depressed form. Like if it actually manages to stay like this, please don't leave it like that when you're done. Actually, like loosen it up. So here's how it works: press in, squeeze in, and what it's doing is it's causing like a vacuum, a lack of pressure. And what should happen if you put this in here is if you press the up button, see how this is causing liquid to get sucked up the tube here. Right, now the problem now is though my bulb is now completely reinflated again. So if that does happen, take it off. Now if I do this, see how the liquid level is dropping back down? Put your thumb on top. There. Now it's not able to do that. Re-inflate it. Top. And then again, if I press the up button like this, see how it's able to draw liquid up the tube? So what you really want to do is get it to the point where you've actually overshot this little line right here. You want to go past it. Make sense so far? Then take it out and press the down button until you can get the meniscus exactly. This is fine hands. I was really lucky. Do you guys see that from where you're at there? How this little curvy section right there, if I were to look at it, the meniscus is right on the bottom. I want to point out another piece for using this tool properly. This is also a very accurate, a very precise tool. This is 10.00 milliliters. Very, very precise, like to less than a drop even. That's how good it is. You have to use it properly. Do you see how as I'm holding it right here, I didn't even mention it because I'm used to this right here. How I pulled the tube out of the water already? If I were to have done that, try this again. I'll draw more liquid back. Up. Show you doing it wrong. So let's say I were to do this. Pull it up to here. Okay, I'm going to leave the tube all the way on the bottom here. I'm going to drop the liquid level. There. Down to there. Does that make sense? And now I'm going to pull the tube out. I don't know if you guys noticed this, but I did have the meniscus at the line right now. Now it's not. Because what's happened, by virtue of it being in the solution, as we were there, it drew some of the solution out of the tube as I pulled it up and out. So make sure that when you do this properly, you overshoot, pull it out of the solution, press the down button until you get it. Chemistry is not neurosurgery. Like, you're not a brain surgeon here, but to some degree, like, there's some similar sorts of skills where if you're able to work really well with your hands, these sorts of fields go all together. I don't know that I've shared with you guys before. My little brother is a dentist, and one of the things that he had to do in order to get into dentistry school was to make carvings out of soap to prove that he had like dexterity in his fingers and hands to be able to work with like really small sorts of things. Imagine being a dentist, right? You're trying to fill just the smallest little cavity, right? And you can't just like hack away at it. You know, like it's got to be, yeah, it's got to be precise, right? So if you're the kind of person who really likes working with your hands, like I do here, there's a lot of fields that really require that, where you have to be exact. You have to be meticulous. So. Okay, so now I should be able to take this guy into here. Now some kids think they should just press the down button until they get all the liquid out, but this is just a smarter idea. Just take the bulb off. And then don't forget, please reinflate it. This one here is working well enough, but it's eventually going to lose its suction, that it won't actually manage to maintain all of its pull. That makes sense? So, they do break over time. So if it's broken on you, please don't feel bad, but if you can, for the sake of my chemistry budget, try not to do things that will break those bulbs. Okay, now what I have is in here I know exactly how much concentrated solution I have. I have 10.00 milliliters of concentrated solute. I know it's not a solid, but didn't I just add a solute to here? Does that make sense? Right. So if our solution is getting diluted, if this is the solute, then the rest has to be the solvent. So again, I'm just adding water the rest of the way. Sure, we don't know what it is, right? And then really this is the same process as we did before. Add water. Again, steady hands helps. Don't overshoot it though. Take it to there. And then use an eye drop. Do it properly. And there's a lot of times in chemistry where it will matter. Right now, since I'm just doing this for the sake of showing it, really, I don't really care all that much, but there are times when, like, literally you should be able to make it go right to the drop. And you'll be like, whoa, that's the one. Like right now, it's too low. Still too low. Still too low. A little bit low. Perfect. Makes sense. And then last step would be to grab some parafilm, put it on top, cap it, and this is how you mix. And now I have two different solutions. This one right here would be my concentrated solution, and this one right here would be my dilute solution. That's two ways of making it. So the first way, take solid stuff, weigh it on the scale. Don't put it directly into there. It's not going to work. Put it into a small beaker. Stir it up with a little bit of water in the beaker. Then pour it inside. Try to get every last particle off of the tools that you used. In theory, that's not possible. Because even this thing right here, my stir stick, there's going to be a few copper 2 sulfate particles that are there. You can even kind of tell, I don't know if you guys can see, but there's a little bit of blue residue right here, right? Hopefully that's really negligible, because if I don't get every particle in there, it affects my accuracy. Does that make sense? But do the best you can. Pour it all in there, use the eyedropper to get it exactly to the line, cap it, mix, now you've got your solution. So that's preparing from a solid. If you are preparing from a liquid and diluting it, use the pipette, put it inside, draw the liquid up past the line, pull it out of the solution, drop it back down to the line, put it in your new container, pull the top off, let it drain out. That makes sense. There's a few other reasons why you might have inaccuracies. Can you guys see how there's a little bit of liquid left inside? That's not ideal either. Probably the reason why is that these things don't get washed very often, but there's probably some other stuff, just a little bit of oils or whatever inside, helping keep the water cling inside, which is less than ideal, because obviously if this right here was supposed to be exactly 10 milliliters, did all 10 milliliters make it out of the tube? Maybe there's like maybe 0.01 of a milliliters left inside. So there are some things that we can't fix. So, does that make sense? Cool. Well, you guys can head back to your seats. Let's talk about this in our notes then. But now that you've seen the visual of it, hopefully that helps. Again, I'm just going to point out here, I grabbed a little bit of paraffin wax to put on top of this guy. Not because I'm worried about evaporation, but in case someone comes in and spills it, now there's not toxic copper 2 sulfate somewhere here, right? Because, I mean, it was poisonous and toxic, causing immediate toxic, poisonous and infectious, causing immediate toxic effects, right? The other thing I should do, I should always do this. When you're done, always make sure you wash your hands. Okay, that's really super important, because I don't want you to be working with some chemicals and a little bit of residue on them, and then you end up, I don't know, eating afterwards. That'd be unsafe. Okay, so let's talk through this in the notes I have here. Okay, so let me talk through my first slide here. I've already kind of given this example here. There's the two ways, right? One way is that you use crystals and water. The other way is you use the dilution method. I need you guys familiar with how to do both. And I promise you, in this year, I'm going to have you guys do a lot of lab work. Okay, let me talk about some terminology. If you ever make a solution with a very accurate concentration, let's focus on that word accurate for a second. How do we know it's accurate? We made it, right? We took time. We were meticulous. We weighed grams on an electric balance, which is a fancy word for a scale. Right? We weighed grams on a scale. We divided that by the molar mass to get us to moles. That makes sense? We can weigh grams on a scale. We'll divide it by molar mass, and it'll get us moles. That's part of what we need to find a concentration. The other part is that we use a volumetric flask, because the volumetric flask will get us liters. If we then take this moles and divide by this liters, we have concentration. And we should know that it's accurate because we spent time measuring it. In the construction world, the phrase measure twice, cut once, you use that at all? Same thing in chemistry, right? Like, make sure that you're meticulous in your measurements, because if not, then you're slightly off. But that's the word we use then, is accurate. So, long story short, we would then call these things a standard solution. Both of the things I just made there, we would call them standard solutions because we know their concentrations. So here's a picture kind of describing what I did, only I don't like this one because this one's not practical. Here, they added the particles directly to the flask, and then they added water and mixed. That might work. But if it doesn't dissolve very well, then you're hooped. Because if you've still got some solid stuff kicking around the bottom of the solution here, you cannot very reasonably put a stir stick inside and expect to stir it up. So the advice I would always give, actually put it into a second beaker first, stir it up, and then pour it inside. Don't actually put the solid directly in the beaker. Now, in the second example I showed you where we dilute things, the term I need you to know is something called a stock solution. If we talk about the really concentrated stuff, that's known as a stock solution. So, in chemistry terms right here, this thing right here is a stock solution. It's the strong, but it's not strong. It's concentrated. So, 2 words I need you to know. Standard solution. Standard solution. You made it yourself. You know it's accurate. It's trustworthy. Okay. You've measured the components. You measured the grams. You converted to moles. You measured the volume. You divided those. You found yourself a concentration. You trust its accuracy. Side note here. There are a lot of solutions that I can pull from the back of the lab where it says on the bottle the concentration is 3 moles per liter. We don't trust that ever. Okay. A couple of reasons why. One, we didn't make it ourselves. Okay. You always need to start from scratch if you're doing something properly in chemistry. Don't take someone else's word for it. If someone says, no, I promise you this is 1 mole per liter, it doesn't matter. Okay? You always need to make it yourself to know that it's trustworthy. And the second reason why it's really important is that even if it was prepared meticulously, what happens to liquids over time? They evaporate, which means that the concentration might slightly change just due to evaporation. Ideally, it's been capped with a lid, but what if it's been left off for half an hour? You get what I'm saying here? So, general rule of thumb, if you want a standard solution, the only way to make one of those and know for sure that it's right, you got to do it yourself from scratch, which sometimes is annoying because you'd like to just go and buy a bottle and say, yeah, this says it's 1 mole per liter. Can I use this? Sorry. Not if you want to do it right. Okay, that's one word. The other word we just mentioned then is stock solution. This is the initial concentrated solution. Now, what I want to show you how to work with here is a formula. This is a formula that you can use to try to figure out how you dilute things. And it's a before-after formula. You have an initial volume, and you have an initial concentration. And if I can go back to my things right here, this, I had an initial concentration, and I took an initial volume of it. I didn't use all of this, right? I only used 10 milliliters of it. So I had an initial concentration, and I took a small volume of it. Afterwards, I have a new concentration. See how it's much lighter, right? It's nowhere near as concentrated as the original one. And the reason why is that what once was 10 milliliters is now 100. And so I'm going to show you how to use some math on the dilution one on the next few slides here. So let's try an example here. Oh, this is basically what we did, only we wouldn't pour it in using a beaker. We would use a much more exact measuring tool. Because, again, using a beaker is pretty... It's like trying to do the fast version of things, which once in a while, you don't need to be exact. Right? Once in a while, you're like, yeah, close enough. Like, for example, let's say you are making juice. On the back of the juice container, it'll say, use 250 milliliters of water for every 3 grams of crystals. You know how like it actually gives a recipe on the back? I don't know about you, but I don't actually follow the recipe. I just take a spoon and I just start scooping it in, and then I just start adding water until it looks good. You know what I mean? Once in a while, sloppy chemistry is okay. It's not the end of the world. But if you want to be exact, don't do this, right? Do what I showed you. So, okay, let's do an example. Let's say that I go to the back of the lab and I get you some 36% concentrate hydrochloric acid. That's really concentrate. Like, that's burn a hole through your jeans. I've actually done that before. Okay. It will dissolve a pop can easily. It will dissolve fabric. It'll corrode your skin. So we're talking strong stuff. Concentrate stuff. Let's say that you don't want to work with 36% hydrochloric acid. That's a little bit too much. Let's say that you only want to make it 10% concentrate. Well, the question is, how much initial HCl should you make? So in a way, what I'm saying is, you've got the really concentrate stuff. I'll even use the examples again. This is 36%. This is now 10%, much safer to work with. You got what I'm saying here? My question is, if this, by the time we're done, is 4 liters, how much should this thing have used? Right? Because this is what took just a small portion of the concentrate stuff. How much should we use to make that work? So here's where that formula comes in. It looks like this. Your initial volume multiplied by your initial concentration is equivalent to your second volume and your second concentration. It's actually a really easy formula to use. Okay, 36% right here. What is that? Which of these 4 variables is this 36%? Yeah, it's your C1. It's your initial concentration. When we began, it was 36% concentrated. But when we're done, we don't want it that concentrated. That's too, for lack of a better word, that's too strong. Strong's not the right word, though, right? We eventually want it to be 10% concentrate. Now, we need to know one more thing, though. We need to know, well, how much do I actually want? Well, it says right here, I want to eventually have 4 liters. So it makes sense that this 4 liters right here is what we're eventually going to have when we're done. So it means my final volume when we're finished is going to be 4 liters. So my question is, how much should you use of the smaller amount of concentrate stuff so that when you're done, you have lots of less concentrate stuff? Well, this is just a one-step calculation. How do you get V1 by itself? Divide by 36% on both sides. V1 is going to be whatever 4 times 10 divided by 36 is. Anybody get an answer? 1.13? 1.1 repeating. Okay. So 1.1 repeating. So let's talk about a few things here then. What units would it be? Look this over. See how there's a percent sign right here and here? Really, your percent signs kind of cancel, don't they? What unit is left? Liters. Okay, let's talk about this for a second here. If I want to make 4 liters of the dilute stuff, doesn't it make sense that I should use a smaller amount of the concentrate stuff? Right? I'm going to use a smaller amount, right? This was a much smaller amount that I started with than when I eventually put it into here, because the rest is water. Second question is about precision. Okay, this right here was precise with 3 sig digits, but these guys right here were precise with 2 sig digs. So I do need to make sure I'm consistent with that. My final answer then is 1.1 liters. So here's what that means. If I start with 1.1 liters of the solute, how much solvent do I need to add to it? See what I'm doing here? I use this formula right here to figure out how much of my solute, the initial amount I started with. And so I calculated I needed 1.1 liters of the solute. But a follow-up question would be, well, how much water should I add? Okay. When I took this thing right here and I added 10 milliliters into here, okay, there's 10 milliliters of the concentrate stuff into here. How much was the rest for water if this adds up to 100? 90. Does it make sense? right? Because if you took 10 milliliters here and put it in here, this is 100, right? So 10 gets you to there, 90 gets you to there. So the reason I want to point this out is I want to make sure it's clear what we solved for. In this formula right here, this volume is the volume of the initial volume of your solute. Okay, but if I were to ask you how much solvent to add, well, we went from 1.1 liters of the strong concentrate stuff to 4 liters. This rest must be the solvent. Does that logic make sense? Okay, let's try another example. Okay, I'm going to give you 14.5 grams of calcium phosphate, and we're going to make it in a solution of a 100.0 volumetric flask, just like I did in our lab today. Here's my question. What is this concentration of this standard solution? I can even use that word now. It's a standard solution because we should exactly know its concentration. Okay, well, how do you find a concentration? Isn't a concentration ultimately equal to a mole divided by a liter? Like, isn't that our goal? Goal is to get 2 moles per liter. Right. So, do I have liters? Well, I guess, right? This volume right here is 0.1000 liters. So I actually have the liters that I need. But I need moles. Do I have moles? Can we measure moles on a scale? Okay, we can't measure moles on a scale, but we can measure grams and then convert to moles. So here's what we're going to do. We're going to take 14.5 grams, and we're going to multiply by a mole per gram, and we're going to find a molar mass of calcium phosphate to get ourselves a moles number. So we have to do one more step. We need to know what the molar mass of calcium phosphate is. What the heck's a calcium phosphate? All right, calcium, Ca, phosphate, PO4. Is that the formula, though? Shaking your head no. Why, Joe? Okay, so what do I need to balance it? Awesome. Okay. If you don't know your vocabulary and you don't know your words and you can't name calcium phosphate, this whole thing blows up, right? Because you're going to need this formula written correctly to get this molar mass, to get this moles, to divide by liters to get our goal. Right? So like if step 1 in the pyramid falls out because you don't know what a calcium phosphate is, it makes it really hard. Okay, calcium is 40.08. You need 3 of them. Phosphorus, I haven't done that one in a while. 3097? 3097? Nice. We'll need 2 of those. Oxygen is 16 on the dot. We need 8 of them. We need to add that up and calculate what the sum of all of this is to get a molar mass of calcium phosphate. If anybody gets it, let me know, by the way. I don't have my calculator out yet. Anybody else confirm that? Cool. Okay. Okay, so I want to make sure I'm not losing anybody here. I know what calcium phosphate is. Step 1. Now that I know what calcium phosphate is, I found its molar mass, which I wrote right here. Molar mass isn't useful on its own, but I can now take the grams number I have, divide by the molar mass, and get me the amount of moles we have, which should be pretty small. So you guys want to take 14.5 grams, divide by that molar mass, and tell me how many moles we were using? Just round it to like 2 decimal places for now. What'd you get? Oh, okay. 14.5 divided by 310.18. Should be small. It should be like 0.046. Okay. Now, I'm going to write down 0.046 on paper, but did you get that too? Okay. I'll write 0.47. Now, I'm going to write 0.47 down on paper, but this is my way of doing things. I put dots afterwards. You guys who took physics with me have already seen me do this before. I do that to remind myself that I'm not going to round this number. Whatever that value is in my calculator, I'm going to use the entire value in my next calculation. Because ultimately, here's what I need to do now. I need to take that 0.047, whatever that value was, the exact value, that's how many moles we have, and I now want to divide it by 0.1000 liters. But don't make it 0.047. You use the exact number that was in your calculator. You guys know how to do that? And if you take that moles and divide by that liters, we'll now get a concentration. Which I should be able to do this in my head. That should make it 0.47 moles per liter. So let me walk you through this process one more time from the top, how this worked. First thing I did, I started here by saying, well, what do I need to get to my goal? In order to get to my goal, I need to know moles and I need to know liters. Liters, I was already told how many liters I was using, because literally that's the size of the flask. Moles is a bit harder. To get moles, I took a molar mass, which came from knowing what calcium phosphate was. I took my mass, I divided by my molar mass to get moles, and then I divided by liters. Rebecca. Keep in mind, though, we put the solute in there first, and then we added the water. It's a really good question, a really good point here. Do not ever add 100 milliliters of water and then add the solute afterwards, because isn't that going to add to its volume ever so slightly? Does that make sense? So in theory, actually, you don't actually have 100 milliliters just of water. You probably have 99 milliliters of water, and the other milliliter of volume is probably taken up from the solid itself. But as a solution, the net volume of all of it's the 100. See the difference of what I'm saying there? Okay. That's a good question, by the way. Okay, in terms of digits then, this guy gave me 3 sig digs. This one gave me 4, and I want to point out why this is so important. Let's say that I didn't use a volumetric flask. Let's say I tried to make this in a beaker and I didn't have 4 digits of precision. It might actually mess up my final answer a little bit. So we always want to have as many digits as possible. So this had 3, this had 4. By the way, this molar mass right here had 5, in case that matters. So in terms of lowest amount of digits, we have 3. So I need some help here. I don't know what came after the 7. You guys want to help me out here? It's 0.4 what? 467 then. Okay, there. Now we know this, and I would call this a standard solution because we made it ourselves. We know precisely and accurately that concentration because we weighed the mass. We tried to get every last particle into the container. Make sense so far? That mass wasn't helpful, but with a quick molar mass calculation, we got moles. Liters we know because we precisely made the volume go right up to the line. And then taking the moles and dividing by liters gives me moles per liter. There's my concentration. These are the sorts of skills I'm going to want you guys to work on over the next little while, is being able to do these sorts of calculations. There really isn't formulas necessarily. You know, I mean, there are some formulas here and there that work, but sometimes you just need to figure out, well, how do I solve this puzzle? How do I work backwards and get myself moles and liters? So, let me try a couple more examples here. I've got 6, right? Okay, let me speed up here because I got 10 minutes left. All right, here we're going to take some water. We're going to add it to a solution until the final volume is 1 liter. We want to find the new concentration of the solution. Well, this is back to the other method of preparing things. This is not starting with solid mass. This is diluting. So in this case here, I do have a formula for you. Your initial volume times by the initial concentration should equal the final volume and final concentration because this is the dilution case. So in this example here, you just need to make sure you put the numbers in the right spot. Do we know the initial volume of what we had? Yeah. We were given a 0.2 liter cleaning solution, so I do know my initial volume. And while I'm talking about it, don't I know my initial concentration? This was my initial volume. This was my initial concentration. Well, when I was done, I know how much volume I had. I had 1 liter of total volume. Side question, how much water did you add? You had 200 milliliters of the cleaning solution, and when you were done, your final volume is 1 liter. How much water did you add? Does that make sense to everybody? 800 milliliters, right? Don't, like when I was saying to Rebecca a second ago, you have to make sure that when you do this here, you don't add 1 liter to the 200 milliliters you have beforehand. Otherwise, your volume's too much. You have to make sure that you add a less amount of water. So this means that you're adding 800 milliliters of water. When you're done, it means you have this much final volume. The question is, well, what's your new concentration? Should your concentration go up or down? Down, right? Because you're diluting it with water, right? It used to be this concentrate. You add water to it, it becomes weaker, right? So, really, to solve this one, you just need to divide by 1. So, what is a fifth of 2.4? You want to have a calculator? 0.2 times by 2.4, and then if you want to, you can divide by 1, I guess. Okay. Is that the right answer? Okay, so a couple of reasons why. First of all, it's precision. This was taken with enough meticulous precision to get us 3 sig digs, 3 sig digs. This one was even more, 4 sig digs. And right here, somehow I end up with an answer with only 2 sig digs. Okay, so did it end up being exactly 0.48? So then throw a 0 on the end. Okay. Second question, what about my units? What units left over? Well, watch this. Right here, this liters kind of cancels with that liters down there. Which unit didn't cancel? This one right here. I mean, it's a combined unit, but the unit of moles per liter. And again, this would now be a standard solution. We now know precisely and exactly this guy's concentration. This stuff right here, by the way, the cleaning solution, the name we would give that is stock solution. Stock solution is the initial concentrate stuff. Standard solution is any solution that we know its concentration because we calculated it. Any questions? Okay, let's try some more examples until I run out of. Let's say that I want you to make a 2 molar solution of sodium hydroxide. Okay? I'm telling you, it has to be exactly this concentrate. Okay? You can't make it too concentrate or too not concentrate. It's not going to work. It has to be exactly this. And I'm going to tell you what size flask you use. You can only use a 50 milliliter volumetric flask. So we're kind of going back to the beginning now and saying, how much solid should you start with? Should you start with 1 gram or 2 grams or 1.3 grams? Can I get how there's a twist on this question here? We're working backwards here. Now, each of these kind of puzzles in terms of math, they require a different way of solving. Here, there's really not a formula I can use because, first of all, this formula here is only for diluting stuff. And I'm not making this solution from diluting, I'm making it from solid crystals. So, I mean, right off the bat, this formula's out. Maybe this is a better way of approaching it here. I always like to start with the non-ratioed value. Can you guys do this calculation in your head real quick and say that that's that many liters? 50 milliliters is 0.500 liters divided by 1,000. I like showing it with ratios. I don't want liters, right? So how do I get rid of liters? Well, let's put liters on the bottom of a fraction. See how that would then cancel out liters? What am I actually looking for? What's my ultimate goal here? Well, I could try to put grams there, but does anybody know what grams to liters conversion? Unfortunately, I don't think we have one, but I have something that's almost as good. I could go moles to liters. Now, I know I wanted grams ultimately, but a moles to liters conversion isn't bad because I have one of those. Isn't that what this number right here is? 0.200. Capital M means moles per liters. So if I multiplied by this, see how my liters would cancel? I wanted grams, but I'll take an intermediary of moles. Because why don't I just do one more ratio? Now let's get rid of moles. So I can cancel out moles and put grams there. My only question is, does anybody know a grams per mole ratio? Sodium hydroxide. Can we look up sodium hydroxide's molar mass? Sodium hydroxide is NaOH. Sodium is 2299. Oxygen is 16. Hydrogen is 101. 1.01. It's actually 40 right on the dot. So this puzzle gets solved a little bit differently here. If I take my liters and multiply by moles per liter, I'm left with moles. But I don't want moles, I want grams. So if I use grams per mole, I can cancel this one right here. I just need to know a grams to mole ratio, which I do, because sodium hydroxide is 40 grams to 1 mole. Can you guys visualize how this works then? This liters cancels this one. This moles cancels this one. Which unit is left over? Grams. Isn't that what I wanted? How many grams of solute you need? So all I need you guys to do is multiply. Can you multiply this one by this one by this one, and I'll tell you how many grams you need. You want to have an answer? Did you finish it? What'd you get? Anybody get something different? Okay. Is that the right number of sig digs? This one needs 3. This one needs 3. This 40.0, by the way, should be taken into account. It had 4, though. So, perfect. Which, in a way, I guess you could say you need 400 milligrams. Right, if you know how to do those conversions, grams to milligrams is a factor of 1,000. So. I gave the example of Melissa's grandparents when they make juice. One of them is really chintzy. One of them is like just keeps pouring the sugar in there, right? Well, when we're working in the chemistry lab, sometimes we have to know exactly how much to start with, right? If I'm giving you these parameters and saying we must have this concentrate in this flask, well, now you know this is exactly how much to put on the scale. Because if you put 402, it's too much. If you put 397, it's too little. Let me try one last example before our bell goes, and then we'll take off, because I think we're running out of time here. In a way, I need you guys to be able to have good problem-solving skills and being able to see this puzzle and go, okay, what sort of skills do I know that can help me solve? And often, it's best just to reverse engineer and look at the end and say, what are we asking you for? Right here, my question is, how much solute will be required? What am I asking you for? Grams, yeah. Okay. I'm asking you for grams. Well, how can I get to grams from the information I have here? And the more you do it, the better you get, but maybe you'll recognize that if I start with liters, liters is a non-ratioed value. If I were then to multiply by a mole per liter, it would cancel those liters. I know it's not quite to the grams that I want, but it's partway there. Because then if I were to use a grams per mole ratio, you see how through this two-step process, I can get liters to turn into moles and moles to turn into grams? All I need is to just fill in the values. So, do I have a liters value? Yeah, 2.0 liters. It was given there, right? How concentrate do I want to make it? 0.16 moles per liter concentrate. Grams per mole, is that going to be given in the question itself? Not explicitly. How do I find a grams per mole, though? Use a molar mass. I have to tell you what we're making, though, right? If I don't tell you that it's potassium chloride, we can't solve this question, right? But since I know it's potassium chloride, potassium is what, 3910? Chlorine is 3545, I believe. 7455, I think. There. Now we have all the information we need. This liter cancels. This moles cancels. We're left with grams. Kids often get really frustrated at the early stages of chemistry because they're like, I want a formula. But it doesn't really work in that same sort of way as physics does, where I can give you formulas. It's more of a puzzle of problem solving. You have to figure out how to piece things together. I think I have just enough time just to show you the last one here. On this last one right here, I just want to show you how this puzzle would get solved. Look at the stem of the question here. It asks you how much solvent should you use. If I'm asking you for how much solvent should you use, what am I actually asking you to find? Liters. Yeah, I'm looking for liters. So let me show you how you might start this one. Maybe start with the one non-ratio number you have, 18.9 grams. If I were then to do moles per gram, can you guys see how the grams would cancel? And then I want liters. If I were to put liters over moles, you see how the moles would cancel? I'm kind of inverting it. I'm starting with grams. I'm doing grams per mole right here. That gets rid of these grams. And then I'm doing liters per mole right here. That gets rid of those moles. See, now I've got liters where I want it. The only thing I'm lacking then is some values. What's the grams to mole ratio? Well, all I need to do is find sodium carbonate's molar mass. I believe I know it. I believe it's 105.99. But do you guys know how to find molar mass well enough by now? What about this one right here, liters per mole? Do I have a liters and moles ratio given? Sure, there's one right there. Where's the 0.67 go though? On the top or on the bottom? Yeah, right, because it's 0.67 liters moles in 1 liter. All right, if you guys can kind of see how this puzzle gets put together here. This grams cancels that grams. This moles cancels this moles, and there's the liter I'm left with. I sure hope that's 105.99. If not, then I've done it wrong. It was? Okay. So, okay, let me stop for the day. Quick summary then, because I know you guys got to take off for your next class. This is the main part of what you guys are going to do on your first quiz. On your assignment, there's a bunch of questions to start practicing these skills. Sometimes they involve formulas. Sometimes they involve using ratios to figure things out. The best advice I can give you, you need practice. Okay? Please call me over, ask me for help as you solve these questions. I started my class by mentioning this. I'm just going to throw you guys right in the fire and give you a quiz on Thursday. Most of it's going to be on this. Okay? And if it doesn't go well, that's fine. But the real key is, can we learn from it going forward? Okay, so tomorrow we're going to do one last lesson. Wednesday we're going to do a lab. Thursday we're going to try a quiz. Friday we're going to go over that quiz. Hopefully it goes well, but if it doesn't, that's why we have Friday for that. So, all right, we'll see you guys later.